Hello friend, hello my student. Today is going to fourth lecture on the specific heat of gases. Okay, so when a gas is heated with volume and pressure change with the increase in the temperature. बघा परत when a gas is heated जेव्हा आपण गॅस हीट केला with volume and pressure change with the increasing in temperature. So amount of it required to rise temperature of 1 gram of gas through 1 degree Celsius is not fixed. Okay. This is this is single specific heat. A gas can have any value of specific heat depending on the condition under which it is heated. Okay. The specific heat capacity is defined as the quantity of heat required to rise the temperature of 1 kg of the gas by 10 Kelvin. So, experiment shows that the temperature rise of liquid due to heat transfer to the water is given by Q is equal to mc in the bracket T2 minus T1. This is equation number 8. So, specific heat of gas where Q is equal to heat transfer to the water, isn't it? Heat transfer to the water is denoted M is equal to mass of water T2 minus T1 is the temperature rise of the water. C is equal to, this is equal to specific heat. In general, the value of specific heat C depends on the substance. So, in general, the value of specific heat depends on the substance in the system. The change of state involved and the particular state of the system at the time of transferring heat. त्या particular time मध्ये काय होईल system मध्ये at the time of transferring heat. Specific heat of solid and liquid is only a function of temperature. Okay? Specific heat of solid and liquid is only a function of temperature, but specific heat at gases substance is a function of temperature and process. Specific heat, specific heat at constant volume. Constant volume is denoted by Cv. Specific heat at constant value is the change of specific internal energy. Right? Specific heat at constant volume is the change of specific internal energy with respect to temperature. When the volume is held constant, then isochoric process. हे काय आहे आयसोकोरिक प्रोसेस आहे काय जेव्हा हीट कॉन्स्टंट असेल आणि व्हॉल्यूम इज चेंज होत असेल ऑफ द स्पेसिफिक इंटरनल एनर्जी विथ रिस्पेक्ट टू टेम्परेचर बरोबर when the volume is held constant and ही जी प्रोसेस आहे this is the isochloric process आहे मग in a CV is equal to in a bracket dV upon dt bracket close into V म्हणजेच काय U means internal energy T is the temperature 9 equation for constant volume process del in a bracket delta U bracket close V is equal to integration of T to T1 then Cv dt. This is equation number 10. Specific heat at constant pressure in a bracket Cp. Specific heat at constant pressure is the change of specific enthalpy. with respect to temperature. Again, specific heat at constant pressure is the change of specific enthalpy with respect to temperature. When the pressure is held constant, then this is the isobaric process. And the Cp is equal to in a bracket delta H upon delta T and into P. Bracket close into P 11. For constant pressure process, delta H in a bracket delta H in P is equal to integration of T2 to T1 then Cp dt. This is equation number 12. Why the Cp is uh, uh, Cp Cp is a greater than Cv. Why the Cp is a greater than Cv? Specific heat at constant value represent the heat supplied to a unit mass of the system to rise the its temperature to 1 degree Kelvin, keeping the volume constant. Since V is a constant, then dV is equal to 0, and the work done by the system W is equal to PdV is equal to 0. The first law of thermodynamics says dq is equal to in a bracket du plus dw. dw की value का है pdv. Put there this value and that is equal to du. Specific heat at constant pressure represent the heat supplied to a unit mass of the system. Right? Specific heat at constant pressure represent the heat supplied to a unit mass of the system to rise its temperature to 10 Kelvin, keeping the pressure constant. The pressure constant होता since P is equal to constant, dV greater than 0 and the work done by the system W is equal to PdV greater than 0. Why the Cp is greater than Cv? The first law of thermodynamics says Q means heat is equal to du plus W. And you know that W, PD, we put this value there, then greater than du. We can see from the above equation, we need a quantity equal to dV unit of heat to rise the temperature by 1 degree Kelvin under the constant volume condition, whereas we need a greater quantity du plus du plus w greater than du unit of heat to rise the temperature by 1 degree Kelvin under the constant pressure condition. Thus, we find that we need more heat to perform the work as PdV not equal to 0, along with to rise the temperature of unit mass of the system through 1 degree Kelvin under the constant pressure condition compared to the heat required to only rise the temperature of same unit mass of the system through the same 1 degree Kelvin and no work is done as PD is equal to 0 under the constant value condition. Hence, Cp is greater than Cv. Okay. Applications of first law of thermodynamics. Let us consider 1 mole of an ideal gas enclosed in a cylinder provided with a fractionless system of area A. Let P, V, and T be the pressure, volume, and temperature of gas respectively. dq is equal to du plus pw. Applications of first law of thermodynamics in isoporic change. An A quantity of heat dq is supplied to the gas to keep the volume of the gas constant. A small weight is placed over the piston. Okay, small weight is placed over the piston. The force apply केला. The pressure and the temperature of the gas increases to P plus dP and T plus dt respectively. This heat energy dq is used to increase the internal energy du of the gas. If heat dq is absorbed at constant value, that is isotope. Change as dV is equal to 0, so gas does not any work, means dW is equal to 0. Then, therefore, PdV is equal to 0 and dQ is equal to CV dt for 1 mole of the gas. Now, so equation first law becomes CV dt is equal to du, is equation number 13. Applications of first law of thermodynamics in for isobaric changes, isn't it? याच्यामध्ये बघा. The additional weight is now removed. जे आपण गेल्या याच्यात आयसोकोरिक मध्ये अप्लाय केलं होतं याच्यामध्ये रिमूव्ह करायचंय काय फोर्स फॉर फ्रॉम द पिस्टन. The pistons now move upward direction and its displacement dx such that the pressure of the enclosed gas is equal to atmospheric pressure P. The temperature of the gas decreases. No? कमी झाला. The temperature of the gas decreases due to expansion of the gas. Now, a quantity of heat dq is supplied to the gas till its temperature becomes T plus D. This heat energy is not only used to increase the internal energy of the gas, but also to do external work in moving the pistons upward direction. Applications of first law of thermodynamics. Now, heat dq is absorbed at constant pressure, then dq is equal to Cp Tt. This is equation number 14. Put the value of du and dq from equation 13 and 14 respectively in equation 12. Then you get Cp dt is equal to Cv dt plus Pdv. या इक्वेशन मधनं is equal to Cv dt is equal to इकडे आणल्यामुळे ते काय मायनस होईल आणि is equal to Pdv होईल. मग त्याच्यातनं काय करायचं dt हे कॉमन काढायचं. मग Cp minus Cv bracket close dt is equal to Pdv. This is equation number 15. For molecules of gas, PV is equal to RT. This is the ideal gas equation. And depositing this equation, then we get PdV plus VdP is equal to RdT. But for the isobaric process, VdP is equal to 0. Above equation becomes PdV is equal to RdT. This equation 16. Putting the value of PdV in equation 15. PdV ची व्हॅल्यू काय आहे वरच्या इक्वेशन मध्ये आपण बघितले तर त्याची व्हॅल्यू काय आहे PVD इज इक्वल टू RT. आणि मग इथली जी व्हॅल्यू आहे PdV ची व्हॅल्यू ते तिथे टाकायची. मग तुम्हाला काय मिळेल Cp minus Cv bracket close dt. Okay, dt is equal to RdT. This equation is 17. Hence, the accompanying equation 15 and 17, then we get Myers relation Cp minus Cv is equal to R. याच्या पुढे is equal to R लिहायचंय. ते सुटून गेलेलं आहे. Then again, here Cp and Cv are molar specific heat capacity of an ideal gas at constant pressure, volume and R and R are universal gas constant. The ratio of Cp and Cv is denoted by gamma. Gamma is equal to Cp upon Cv. हा ratio घेतला. This is equation number 18. And now indicator diagram, PV diagram. याची डेफिनेशन जरी एवढं जरी लिहिलं तर 2 मार्काला विचारतात आणि 4 मार्काला किंवा 3 मार्काला एक पूर्ण लिहावा लागतो. बघा इंडिकेटर डायग्राम कशाला म्हणतात? अ कर्व shows variations of pressure, variation of pressure, substance taken. बघा, a curve shows a curve showing the variations of volume of substance taken along the x-axis. काय केलेलं व्हॉल्यूम हा एक्स ऍक्सिसला घेतलेला आहे आणि प्रेशर हा वाय ऍक्सिसला घेतलेला आहे and is called the indicator diagram, PV indicator diagram. The shape of the indicator diagram shall depend on the nature of the thermodynamical process the system undergoes. Okay. Let us consider 1 molar of ideal gas enclosed in a cylinder fitted with the perfectly fractionless piston. Let P1, V1 and T1 be the initial state of the gas. So, show this figure. X ऍक्सिसला व्हॉल्यूम आहे आणि वाय ऍक्सिसला प्रेशर आहे. त्याच्या सायकल बघा ए बी सी हे पहिला डायग्राम एरिया आहे आणि नंतर ए डॅश बी डॅश सी डॅश डी डॅश हा दुसरा वर्किंग एरिया आहे. तर बघू आपण इफ डीव्ही इज द infinitely small increasing in volume of the gas during which the pressure P is assumed to constant, then the small amount of work done is given by the gas is dW is equal to PdV. In the indicator diagram, dW, the work done, is equal to area under the curve A dash, B dash, C dash, D dash. The total work done by the gas during expansion from V1 to V2 is which is equal to area ABCD in the indicator diagram. Total integration is equal to V1 to V2 PdV is equal to area ABCD. Hence, in an indicator diagram, area under the curve represents the work done as shown in a figure. So work done is thermodynamically changed. Consider 1 mole of perfect gas. Work done during the thermodynamically change. Consider that 1 molar of perfect gas is taken in a cylinder having perfectly conducting walls and bottom provided with a piston. Let the cylinder be placed on a source of heat at temperature T degrees Celsius. If the piston is now moved slowly outward direction, the gas expands, does some work and tend to cool, but it absorbs required amount of heat from the source to keep it at the same temperature. The work done during an infinite small change in volume dV is given by work done is equal to PdV. For finite change in volume from V to V1 to V2, analytic, analytic, analytically, we can be calculate integrating dW between the limit V1 to V2.